Hello everyone and welcome to another episode on this very channel. In today's lesson, we want to look at directional derivatives. If you haven't subscribed to my channel, kindly hit on the subscribe button for me. Directional derivatives help us to understand how a function changes in a particular direction. And actually, PDEs are directional derivatives. In today's lesson, our main focus is going to be on how we can solve a partial differential equation which is a directional derivative of this very form. AUX plus BUY is equal to 0 where A and B are constant. A and B are the coefficient of UX and then coefficient of UY. And then A and B are also not equal to 0. Now U is what our unknown function. And then AUX plus BUY is what the directional derivative. So this part is called the directional derivative. And it moves in the direction of the vector A and B. So in today's lesson, we'll be looking at a PDE of this well form. AUX plus BUY is equal to 0 where A and B are constant. And the quantity AUX plus BUY is the directional derivative. Now let's look at examples of PDE of this very form. So all these PD that I have written down here are of this well form. We have AUS plus BUY is equal to 0 where A and B are constant. So you can see that with this particular equation, our constant is what 1. And we have UX plus what UY, our constant is 1. So when you look at the rest, you can see that we have a constant, the coefficients are constant, the coefficients are constant, the coefficients are constant. So all these PD are of this very form. So we have, now let's look at these PDEs carefully. You can see that all these PDEs are linear. They are linear. They are linear. And they are of a first order 2. You can see that all of them are order 1, and then order 1. And they are homogeneous as well. So all these PDEs are first order linear homogeneous PDE with constant coefficient. They are what? So as I said earlier on, all these PDEs are first order linear homogeneous PDE with constant coefficient. And mostly first order linear with constant coefficient are directional derivatives. Now how do we solve a directional derivative? So when you have a PDE which is a directional derivative, the general solution is given as a function of what bx plus what ay. Then we negate any one of them. So let's negate the first one. Very, very easy and then simple. We can also write it in this very form. So we have a function of bx minus ay. This and that will give us what the same solution. So with the first one, we negated bx. And then with the second one, we negated what? Ay. The most important thing is one of them has to be negative, or we have to negate one of them. And what we did here also is that we multiply y by the coefficient of what ux. So we multiply y by the coefficient of what ux. And then we multiply x, this one, by the coefficient of what? Of uy. So what we have to do is to multiply y by the coefficient of ux and then multiply x by the coefficient of what? Uy. Very, very easy and then simple. Now that we know this, let's find the general solution for some of these PDEs here. So this is one of our general solution. So we want to find the general solution for this PDE. Very, very easy and then simple. As we said, this is a directional derivative PDE. So the general solution is of this well form. So first we have our PDUX plus what UY is equal to 0. And we are saying that the general solution is of the form a function of bx minus what? AY. So from here, our A is 1 and then our B is also 1. So we are just going to plug them into this. So we have a function of our A, our B is 1, so we have x minus what? Y. And this becomes the general solution for this particular PDE. Very, very easy and then simple. Let's look at the next one, which is II. So our general solution is going to be u of xy. We have a function of. So from here, our A is equal to what? 4. And then our B is equal to what? Minus 3. So once we have that, we are just going to plug it in place of any one of these. So we are going to have our B is minus 3. So we have minus 3x and then plus what? Our A is what? 4. So we have 4y. Now once we have this, we negate any one of them. So let's negate the first one. So we have a function of this will give us 3x plus what? 4y. Very, very easy and then simple. Very, very easy and then simple. So general solutions to directional derivatives are very easy and then simple. Now let's look at the ones that involves initial condition or auxiliary condition. We want to solve this PDE 4ux minus 3uy is equal to 0 with the auxiliary condition u of 0y is equal to what? Y cube. So you can see that this PDE is of the form AUX plus BUY is equal to 0. And the general solution for a PDE of this well form is given as what? Is given as u of xy is equal to a function of bx minus what? AY. This is a directional derivative. The quantity 4ux minus 3uy is a directional derivative with constant coefficients, and therefore the general solution will be given as that. So you have our general solution u of xy is equal to. So from here, Ra is equal to 4, and then our B is equal to what? Minus 3. So we have our function, our general solution is what? A function of minus 3x minus what? Our A is 4, so we have 4y. Very, very easy and then simple. As I said, the most important thing is to multiply y by the coefficient of what? X, and then multiply what? X by the coefficient of what? Y. Very, very easy and then simple. And once you are done, you negate one of them. So this is the general solution and we are done. So it's what? The general solution. This is the general solution. Now because we are being given an auxiliary condition, we have to continue to find the particular solution. So we have to find what the particular solution. With the particular solution, this is the initial condition given or the auxiliary condition given. So we have u of 0y is equal to what? Y cube. So this means that wherever we see x in the general solution, we have to replace it with what? 0. So you can say that our x is equal to 0 and then our y is also equal to what? Y. So we are going to put this in the general solution. So we have our u of 0y is equal to negative 3 times 0 give us what? 0. So we have 0 and then we have minus 4y. So we have u of 0y is equal to y cube and then u of 0y is equal to a function of minus 4y. If you have, let's say, two equations, let's say p is equal to 0 and q is equal to 0. since this is equal to 0 and then this is also equal to 0, we can say that P is equal to Q. So from here, we can say that y cube is equal to a function of minus 4y. So we have minus 4y is equal to what? Y cube. So at this very point, what we are going to do is that we are going to find out what happened to minus 4y that gave us what? Y cube. What happened to what? Minus 4y that gave us what? Y cube. So what we are going to do is we are going to let any variable at all, let's say p, to represent what is in the bracket of the function f. So we have minus 4y. Then from here we make y the subject. So we are making y the subject. We are going to get p minus p all over 4. Very, very easy and then simple. So once you have your p is equal to minus 4y and then your y is equal to minus p over 4, we come and substitute this into this equation. So we have f of p, f of what? P is equal to, so we have y cube, and we are saying that y is what? Minus p over 4. So we are going to have minus p all over 4 all raised to the power of what? 3. Very, very easy and then simple. So we came for this equation, then we plug in this information. Once we reach this very point, what we are going to do is to go back to the general solution. So this very part, we go back to what? The general solution. So we come to the general solution here. So we are going to pick what is in the bracket here. That is the function of minus 3x minus 4y. We come and put it in place of what? P. So we have our f of what? Minus 3x minus 4y. So we are saying that this p is what? Minus 3x minus 4y. So wherever you see p as well, we are going to replace it with this. So we are going to have minus 3x minus 4y all over what? 4. And all of this is raised to the power of what? 3. Very, very easy and then simple. So from here, we can write it as 3x plus 4y raised to the power 3 all over 64. So therefore, the particular solution for the given PDE with the auxiliary condition, this is what? 3x plus 4y raised to the power 3 all over 64. Very, very easy and then simple. Let's look at another example. We want to look at this example. We want to solve the PDE 2ux plus 7uy is equal to 0 with this initial or auxiliary condition. So looking at this quantity, you can see that it's a directional derivative, and therefore this PDE becomes a directional derivative PDE, and it is of the form aux plus buy is equal to 0. And we said that whenever you have a first order linear homogeneous PDE with constant coefficients of this very form, the general solution is given as what? Is given as u of xy is equal to a function of bx minus what? Ay. Very, very easy and then simple. So from the equation, our a is what? 2, and then our b is equal to what? 7. So our general solution becomes a function of our b is 7, so we have 7x minus what? 2y. Very, very easy and then simple. So this is our general solution. As I said, the most important thing is to multiply y by the coefficient of x by the coefficient of y, and then you are good to go, and then you negate one of them. So we are negating this part. Since we are being given an initial condition or zero condition of u of 0y is equal to cos square 2y, we have to continue to find what the particular solution. So this becomes our general solution. This is our general solution. So let's move on to the particular solution. So we have particular solution. A particular solution. So we have the initial condition, u of what? 0, y is equal to cos squared 2y. So this means that wherever we see x in the general solution, we have to plug in what? 0. So we have the general solution u of 0y. So this is the general solution. We are going to plug in 0 to wherever we see what? X. So we have 7 times 0 give us what? 0. And then we have minus 2y. So we have u of 0y is equal to cos squared 2y. And then we have u of 0y is equal to a function of minus 2y. So you can therefore say that this is equal to that. So we have a function of minus 2y is equal to what? Cos squared 2y. Very easy, and then what? Simple. So from here, as I said, we want to find out what happened to minus 2y. That gives us cos squared 2y. So we are going to let the variable p be equal to what? What is in this bracket? Minus 2y. So from here, we make y the subject. We have y is equal to p minus p all over what? 2. So once we have this, we come back to this equation, and then we plug in this. So we have f of, we said that our minus 2y is equal to p. So we have f of p is equal to, we have cos squared 2y. So we have cos, our y is what? Minus p all over what? 2. So from here, you can see that these two cancel these two. We have our f of p is equal to what? Cos squared minus p. So once we reach this 0 point, we go back to the general solution, and then we pick what is in the bracket of the function. So we have this one, we're going to pick this one. So we have our f of 7x minus 2y is equal to cos squared. We have minus here, and this p is what? 7x minus what? 2y. So we have cos squared. When we expand, we are going to get 7x plus what? 2y minus 7x plus 2y. So therefore, the particular solution to this PDE with the auxiliary condition is given as u of xy is equal to this 2y minus 7x. Very easy and then simple. This brings us to the end of today's lesson. See you tomorrow. Bye bye.